Jupiter is not a planet the way Earth is a planet. The comparison itself is almost insulting to the scale of what Jupiter actually is. When astronomers in textbooks place Earth and Jupiter side by side in the same diagram, they are doing something quietly misleading. They are suggesting that these two objects belong to the same category of thing. They do not. Not really. Earth is a rocky, dense, chemically complex world with a crust you can stand on, an atmosphere thin enough to see through, and a diameter of roughly 12,700 kilometers. Jupiter's diameter is 139,820 kilometers. If Earth were the size of a grape, Jupiter would be the size of a basketball. Not a slightly larger grape, not a grapefruit, a basketball. And that comparison only captures size. It says nothing about mass, about internal structure, about the forces operating inside that world right now, at this very moment, as you listen to this. Jupiter contains more than twice the mass of every other planet in the solar system combined. Read that again. Every planet, Saturn, Uranus, Neptune, Mars, Venus, Mercury, Earth, add them all together, and Jupiter still outweighs that entire collection by a factor greater than 2. The solar system does not have 8 roughly comparable planets orbiting a star. It has a star, one dominant body that nearly became a second star, and then a collection of smaller objects ranging from the merely enormous to the nearly microscopic by comparison. The architecture of our solar system is not a democratic arrangement of worlds. It is Jupiter's system. We simply live in it. What does that actually mean for the ground beneath your feet right now? More than most people ever consider. Jupiter's gravitational influence reaches across hundreds of millions of kilometers of space and touches every object in the solar system, including Earth. The asteroid belt, that broad ring of rocky debris between Mars and Jupiter, exists in its current fragmented state, in large part because Jupiter's gravity prevented those rocks from ever coalescing into a full planet. Every time a piece of that belt gets nudged toward the inner solar system, Jupiter's gravity is part of the equation. Some of those nudges send objects toward Earth. Jupiter, in some configurations, acts as a shield, capturing or deflecting potential impactors. In others, it acts as a slingshot, accelerating debris inward. The relationship is not simple. It is not purely protective. It is gravitational dominance, indifferent to outcomes, operating across geological timescales. The comet Shoemaker-Levy 9 made that dominance visible in a way no diagram ever could. In July of 1994, over the course of 6 days, the fragmented remains of that comet crashed into Jupiter in a sequence of 21 individual impacts. The largest impact events released energies estimated at 600 times the total nuclear arsenal of Earth. Each impact scar left in Jupiter's upper atmosphere was larger than the entire diameter of Earth. Those scars, dark, swirling patches of disturbed cloud, were visible to amateur telescopes from the ground. People watched from their backyards. They watched Earth-sized bruises appear on another planet in real time. The event was the first collision between two solar system bodies ever observed and predicted in advance. And it happened on Jupiter because Jupiter is what Jupiter is. An object so gravitationally dominant that it can capture a comet, tear it into 21 pieces across its tidal forces, and then consume it over 6 days without any lasting structural consequence to itself. That last part is worth sitting with. 21 comet fragments, energy 600 times the global nuclear arsenal, and Jupiter simply absorbed them. The scars faded within months. Now step back even further, because the scale problem with Jupiter does not begin and end with its size. It begins with a question about its nature that most people never think to ask. What is Jupiter actually made of? The answer sounds simple in a textbook. It is a gas giant, composed mostly of hydrogen and helium. But that phrase, gas giant, does something cognitively damaging. It makes Jupiter sound like a large balloon, like something insubstantial, like something you could, in some science-fictional sense, fly through. That picture is not just incomplete, it is wrong in ways that matter. Jupiter has no surface, not in the way that sentence is usually meant. There is no point at which you would encounter solid ground, but that is not the strange part. The strange part is what happens as you descend into Jupiter's atmosphere, as pressure increases, as temperature increases, as you go deeper and deeper through bands of cloud and gas. The hydrogen does not simply compress, it changes. At a depth of roughly 20,000 kilometers below the cloud tops, under pressures exceeding 1 million times Earth's atmospheric pressure at sea level, hydrogen undergoes a phase transition into a state that does not occur naturally anywhere on Earth's surface. It becomes metallic. Liquid metallic hydrogen, a phase of matter in which hydrogen atoms are compressed so tightly that their electrons are no longer bound to individual nuclei. They flow freely. The interior of Jupiter, through most of its volume, is not gas. It is a vast, churning ocean of electrically conducting liquid metal. That ocean of metallic hydrogen is what generates Jupiter's magnetic field. And Jupiter's magnetic field is not like Earth's magnetic field. Earth's magnetic field extends roughly 65,000 kilometers into space on the sunward side, a protective bubble that deflects the solar wind and makes life on the surface possible. Jupiter's magnetosphere extends roughly 750 million kilometers in the direction away from the sun. If you could see Jupiter's magnetic field with your naked eye from Earth, it would appear larger in the sky than the full moon, despite Jupiter being hundreds of millions of kilometers away. The largest structure in the solar system is not Jupiter itself. It is the invisible magnetic environment Jupiter creates around itself. Inside that magnetosphere, charged particles are accelerated to tremendous velocities, creating radiation belts far more intense than anything Earth possesses. Europa, one of Jupiter's moons and a world with a subsurface ocean that scientists regard as one of the most promising locations for extraterrestrial life in the solar system, orbits inside those radiation belts. The surface of Europa receives radiation doses of roughly 540 rem per day. A fatal dose for a human being is approximately 300 to 500 rem total. Europa's surface is being continuously bombarded by radiation energetic enough to chemically alter the ice, split water molecules, and create oxidants that may, through processes still being studied, trickle down into the ocean below. Jupiter is simultaneously the reason Europa's ocean may be chemically interesting, and one of the reasons reaching and studying that ocean presents extraordinary engineering challenges. This is the nature of Jupiter's relationship to the solar system. It does not simply occupy space. It structures space. It alters the trajectories of comets and asteroids across millions of years. It generates the largest magnetic structure orbiting the sun. It shapes the chemical environments of its own moons. It may have been responsible, through the gravitational choreography of the early solar system, for the architecture of the inner planets, including the position and conditions of Earth. The question of whether Jupiter ultimately helped make complex life on Earth possible, or whether it has been periodically directing threats toward the inner solar system, or whether both of those things are true simultaneously, that question has no clean answer. The data point in several directions at once. The models are contested, and the more closely researchers examine Jupiter's role in the history of this solar system, the more uncomfortable it becomes to assign it any simple narrative role. Because the most unsettling thing about Jupiter is not its size. It is how much it has been shaping the story of this solar system, including Earth's story, in ways that went completely unrecognized for most of human history. And even now, with spacecraft having visited it, having plunged probes into its atmosphere, having mapped its magnetic field and its moons and its interior through gravitational measurements, there remains a region at the very center of Jupiter that no instrument has ever directly measured. A core whose exact composition and state remains genuinely, actively debated among planetary scientists. A heart of a world that has dominated this solar system for 4.5 billion years, and that we still cannot fully see. What is at the center of Jupiter? And why does the answer challenge something fundamental about how planets are supposed to form? There is a storm on Jupiter that has been spinning continuously for at least 193 years, possibly much longer. A single storm. One unbroken atmospheric event that has persisted since before the American Civil War, before the invention of the telephone, before the first electric light bulb was ever switched on. It was already churning when Charles Darwin published On the Origin of Species. It was already ancient when the Wright brothers lifted off at Kitty Hawk. And right now, as you listen to this, it is still there, rotating counterclockwise at the same latitude in Jupiter's southern hemisphere, completing one full revolution of its internal winds approximately every 4 to 6 Earth days. The Great Red Spot. Its current diameter is approximately 16,500 kilometers. That is larger than the entire diameter of Earth. A storm larger than our entire planet, and it is not Jupiter's most extreme atmospheric feature. It is simply the most visible one, the one human eyes have tracked longest, the one that has become the unofficial symbol of a world that refuses to behave by any rules familiar to terrestrial meteorology. Wind speeds at the outer edge of the Great Red Spot reach 432 kilometers per hour. To put that in terms of something measurable on Earth, the most powerful hurricane ever recorded on this planet, Hurricane Patricia in 2015, peaked at 345 kilometers per hour. Patricia devastated coastlines, made global news, and dissipated within days. The Great Red Spot has sustained winds stronger than Patricia continuously for nearly 2 centuries. And unlike a hurricane, which is a low-pressure system that draws energy from warm ocean water and collapses the moment it moves over land or cold sea, the Great Red Spot is a high-pressure anticyclone. It does not need a warm ocean. It does not need a surface at all. It draws its energy from Jupiter's own internal heat and from the constant interaction of the jet streams that bracket it to the north and south, grinding against it, feeding it, keeping it alive across timescales that make human civilization look momentary. The question of how long this storm has actually existed is more unsettling than it first appears, because the historical record is genuinely fractured. In 1665, the Italian-French astronomer Giovanni Domenico Cassini turned his telescope toward Jupiter and recorded a dark oval feature in the planet's southern hemisphere. He tracked it for years. Other astronomers of that era observed it as well, and it was documented continuously at that latitude until 1713, when it simply vanished from the record. No explanation, no gradual fading that anyone noted. It was there, and then it was not. For 118 years, the historical record contains no confirmed observation of a storm at that location. Then, in 1831, astronomers reported a dark spot at the same latitude. By the 1870s, it was being described as distinctly red. For generations, the assumption was straightforward. Cassini's 17th century storm and the 19th century Great Red Spot were the same object, one continuous system that had simply gone unobserved for a century, perhaps fading in contrast during that gap. It was a clean narrative, reassuringly simple, a storm that had been raging since the age of Newton. A 2024 study published in Geophysical Research Letters by Agustín Sánchez La Vega and colleagues dismantled that narrative with precision. The research team analyzed historical records of the size, drift rate, and positional motion of both Cassini's 17th century permanent spot and the post-1831 Great Red Spot. The two storms do not behave like the same object. The permanent spot moved at a different drift rate along its latitude. The historical size evolution of the two features does not match when extrapolated through the gap. Numerical simulations of how the current Great Red Spot most likely formed, from a flow instability between the opposing zonal jet streams north and south of it, produce a storm consistent with an origin in the early 19th century, not the 17th. The conclusion of the study is that Cassini's permanent spot and the current Great Red Spot are almost certainly two different storms. The first disappeared sometime after 1713. The second formed around 1831 by a separate atmospheric mechanism entirely. This raises an immediate and deeply uncomfortable question. If the most prominent and persistent storm in the solar system can simply disappear, not weaken gradually, not shrink to a remnant, but drop out of the historical record entirely, what does that tell us about the long-term stability of Jupiter's atmospheric dynamics? And what does it imply about the current Great Red Spot, which has been measurably, undeniably shrinking for decades? The numbers are unambiguous. Historical observations from the late 1800s measured the Great Red Spot at approximately 41,000 kilometers on its long axis. When NASA's Voyager 1 and Voyager 2 flew past Jupiter in 1979, they measured it at 23,000 kilometers. Hubble Space Telescope measurements in 2014 recorded it at approximately 16,500 kilometers. The storm that was once wide enough to fit 3 Earths side by side is now wide enough to fit roughly 1 1/3. It has lost more than half its diameter in less than a century and a half, and the rate of shrinkage is not constant. There have been periods of accelerated contraction that researchers are still working to fully understand. Amy Simon of NASA's Goddard Space Flight Center and her colleagues identified one potential mechanism: small eddies in the surrounding atmosphere feeding into the storm and disrupting its internal dynamics. These are not large vortices. They are relatively small atmospheric disturbances, but they interact with the outer boundary of the Great Red Spot in ways that appear to alter the energy balance of the system. Whether these eddies are net contributors to the storm's longevity or net drains on its structural integrity is a question that current models have not yet resolved conclusively. What the data does show is that the Great Red Spot is not simply a static feature embedded in Jupiter's atmosphere. It is a dynamic system in continuous negotiation with the jet streams that surround it, exchanging momentum, shedding material at its edges, and responding to perturbations that originate hundreds of kilometers away in atmospheric layers above and below its main vortex. The storm has an altitude extent that researchers estimate reaches roughly 500 kilometers vertically through the Jovian atmosphere. Its clouds sit at pressure levels of about half an atmosphere by Earth standard, the zone of ammonia ice clouds that gives Jupiter its pale upper haze. But the storm's influence reaches both upward into the stratosphere and downward into much denser, much hotter layers beneath. The color is its own unresolved problem. The Great Red Spot is red. That seems obvious. It is called the Great Red Spot. But the chemistry responsible for that coloration has not been definitively identified after decades of spacecraft observations. The leading hypothesis, supported by laboratory experiments conducted in the years following the Cassini spacecraft's Jupiter flyby in 2000, proposes that the reddish hue comes from complex organic molecules, specifically ammonium hydrosulfide and possibly certain hydrocarbons, that have been lofted to high altitude by the storm's powerful updrafts and then chemically altered by ultraviolet radiation from the sun. The storm acts like a slow chemical reactor, drawing material up from deeper, warmer atmospheric layers, exposing it to solar radiation at altitude, and producing chromophores, color-generating compounds, whose exact molecular identity remains a subject of active research. Beneath the Great Red Spot's visible cloud deck, the story changes completely. The Juno spacecraft, which has been in orbit around Jupiter since 2016 and has made repeated close passes over the storm, carried a microwave radiometer instrument capable of probing Jupiter's atmosphere to depths far below what any camera can see. The data revealed that the Great Red Spot's roots extend at least 350 kilometers below the visible cloud tops, possibly deeper. At that depth, temperatures are significantly higher. Pressures are measured in tens of Earth atmospheres, and the composition of the atmosphere shifts away from the ammonia-dominated chemistry of the cloud tops into something more complex, more chemically active, and more poorly understood. 350 kilometers of vertical extent for a single storm. To calibrate that, the distance from the surface of the Earth to the boundary of space, the Kármán line, is 100 kilometers. The root structure of the Great Red Spot reaches down through a distance 3.5 times the entire height of Earth's atmosphere. Every spacecraft that has visited Jupiter has returned data that deepens the inventory of what is not understood about this storm. Voyager gave humanity its first close look at the swirling cloud structure in 1979 and raised more questions than it answered about the energy source sustaining the vortex. Galileo, which orbited Jupiter from 1995 to 2003, added atmospheric composition data and confirmed the layered complexity of the cloud system. Juno, the most recent and most capable orbiter, has probed deeper than any previous mission. And the picture that emerges is not one of an increasingly well-understood phenomenon. It is a picture of a storm whose three-dimensional structure, energy budget, color chemistry, long-term fate, and relationship to Jupiter's interior all remain open questions in active planetary science literature. The Great Red Spot may survive for another century. It may collapse within decades. The models that attempt to predict its future behavior disagree. And the reason they disagree is rooted in something deeper than insufficient data. It is rooted in the fact that Jupiter's atmosphere is coupled to an interior that no instrument has ever directly sampled. An interior whose structure, composition, and energy output feed into every atmospheric process on the planet, including the one that has kept this storm alive for nearly 200 years. The atmosphere is only the surface of the problem. Beneath those cloud bands, beneath the Great Red Spot's 350-kilometer roots, beneath the metallic hydrogen layer, something sits at the very center of this planet that planetary scientists have been debating for decades. And the debate is not about minor details. It is about whether Jupiter even has a core in the way that word is usually understood, or whether the Juno spacecraft's gravity measurements have revealed something at the center of Jupiter that defies every model of how planets are supposed to form and evolve. Jupiter formed 4.5 billion years ago, before Earth existed, before the Sun had finished settling into its current stable state, in a protoplanetary disk of gas and dust that surrounded a young star still contracting under its own gravity. The process that built Jupiter was not the same process that built Earth. It was faster, more violent, and governed by a different set of physical thresholds. Thresholds that Jupiter crossed, and Earth never came close to reaching. The leading framework for Jupiter's formation is called core accretion. The model works in stages. First, solid particles of rock and ice in the outer solar system, beyond what planetary scientists call the snow line, the orbital distance at which water ice becomes stable, began colliding and sticking together. Over hundreds of thousands to millions of years, these collisions built progressively larger bodies, dust grains to pebbles, pebbles to boulders, boulders to planetesimals kilometers across, planetesimals to a growing protocore. When that core reached somewhere between 5 and 20 Earth masses, models disagree on the precise threshold, something changed. The core's gravitational field became strong enough to begin capturing not just solid material, but the gas of the surrounding nebula itself, hydrogen and helium, the two most abundant elements in the universe. At first, the gas accretion was slow. The growing envelope radiated energy away as it compressed, and that energy loss kept the infall gradual. But there is a critical mass at which the system tips. Once the mass of the gas envelope roughly equals the mass of the solid core, the envelope can no longer support itself in hydrostatic equilibrium. Gravity wins. The gas collapses inward rapidly, not over millions of years, but over thousands. Jupiter's enormous hydrogen and helium envelope, which accounts for roughly 95% of its total mass, was acquired during a runaway collapse phase that may have lasted only a few thousand years. A few thousand years to accumulate the bulk of the most massive planet in the solar system. In geological terms, that is not gradual. That is nearly instantaneous. This is precisely why Jupiter is so massive, and the other giant planets are not. Saturn, Uranus, and Neptune all formed later, in a protoplanetary disk that was already being depleted by Jupiter's own formation and by the increasingly powerful radiation from the young Sun. They underwent similar core accretion processes but never triggered the same runaway collapse at the same scale. Saturn's gas envelope is substantial, but less than a third of Jupiter's total mass. Uranus and Neptune are classified as ice giants rather than gas giants. Their bulk composition is dominated by water, methane, and ammonia ices rather than hydrogen and helium gas, because they formed in a region of the disk where temperatures were low enough for those compounds to remain solid and where the available gas was already thinning by the time their cores reached the accretion threshold. Jupiter got there first. Jupiter got there fastest. And the consequences of that priority ripple through every aspect of solar system architecture. Now consider what 4.5 billion years of self-compression does to a body of this mass. Jupiter emits more energy than it receives from the Sun. This is not metaphorical or approximate, it is a measured physical reality. The Cassini spacecraft, during its Jupiter flyby in 2000, confirmed measurements showing that Jupiter radiates approximately 1.67 times more energy into space than it absorbs from solar radiation. The excess energy comes from gravitational contraction. Jupiter is still slowly shrinking, compressing under its own weight, converting gravitational potential energy into thermal energy that radiates outward through its cloud layers. The rate of contraction is approximately 2 centimeters per year, invisible on human timescales, physically significant across billions of years. Since its formation, Jupiter has contracted from an initial radius estimated at roughly twice its current size. That internal heat engine drives everything visible on Jupiter's surface. Earth's weather is powered primarily by solar energy. Differential heating of the surface and atmosphere by sunlight drives the winds, the storms, the jet streams. Jupiter receives 27 times less solar energy per unit area than Earth, yet its atmospheric dynamics are far more energetic, far more organized, and far more persistent. The source is not the sun, it is Jupiter itself, radiating heat upward from its interior through convective columns of gas that reach through tens of thousands of kilometers of atmosphere and organize at the cloud top level into the iconic banded structure of alternating light zones and dark belts. The zones are regions of upwelling, warmer gas rising from below, cooling as it expands at altitude, forming the bright ammonia ice clouds that give them their pale appearance. The belts are regions of subsidence, cooler gas sinking back downward, clearing the upper cloud layers and revealing the darker, warmer chemistry beneath. Between every adjacent zone and belt runs a powerful jet stream, a band of horizontal wind shear that can reach speeds of over 500 kilometers per hour. Jupiter has more than 24 such jet streams. They are extraordinarily stable across centuries of observation. Unlike the jet streams of Earth, which meander north and south seasonally and are disrupted by the presence of continents and ocean temperature gradients, Jupiter's jet streams are locked to fixed latitudes with a rigidity that current fluid dynamics models struggle to fully explain. The reason for that rigidity is connected to something deep in Jupiter's interior, specifically to the behavior of the metallic hydrogen layer. At roughly 20 to 30,000 kilometers below the cloud tops, as pressures exceed 1 million Earth atmospheres and temperatures reach approximately 10,000 Kelvin, hotter than the surface of the sun, hydrogen transitions into its metallic state. This is not a sharp boundary like the surface of a rocky planet. It is a gradual transition zone in which hydrogen molecules are first broken apart into individual atoms, and then those atoms are compressed until their electron clouds overlap and electrons begin moving freely between nuclei, creating an electrically conducting fluid. The transition from molecular to metallic hydrogen happens across a depth range of thousands of kilometers and represents one of the most extreme phase transitions studied in high-pressure physics. Laboratory attempts to recreate metallic hydrogen on Earth require apparatus capable of generating pressures of several million Earth atmospheres instantaneously, typically through laser-driven shock compression of tiny hydrogen samples. These experiments last for fractions of a microsecond and have confirmed the existence of the metallic state. But the conditions inside Jupiter persist across a volume of space so large that Earth itself could fit inside it with room to spare, maintained continuously for 4.5 billion years. No laboratory on Earth can replicate that volume, that duration, or that pressure in any sustained way. The flowing metallic hydrogen generates Jupiter's magnetic field through a dynamo mechanism. Convective motion in the electrically conducting fluid, driven by Jupiter's rapid rotation and its internal heat, organizes into large-scale current systems that produce a coherent global magnetic field. Jupiter rotates once every 9 hours and 55 minutes, the fastest rotation of any planet in the solar system, and that rapid rotation is critical to the dynamo's efficiency. The Coriolis forces generated by this fast spin organize the convective flows in the metallic hydrogen into columns aligned with the rotation axis, producing a magnetic field that, at Jupiter's cloud tops, is between 4 and 14 times stronger than Earth's surface field depending on location. That variation is itself significant. Jupiter's magnetic field is not a clean dipole, not a simple north-south magnetic alignment like a bar magnet, which is roughly how Earth's field is organized at large scales. Juno's magnetometer measurements, published in 2018, revealed that Jupiter's magnetic field is strikingly asymmetric. The northern hemisphere's field is considerably different from the southern hemisphere's in both strength and structure. There is a localized region near the equator in the northern hemisphere where the field lines point in the opposite direction to what a dipole field would predict, a feature that researchers have called the Great Blue Spot, an intense concentration of inward-pointing magnetic flux. Its existence implies that the dynamo generating Jupiter's field does not operate uniformly throughout the metallic hydrogen layer. There may be a shallow dynamo operating in the transition zone between molecular and metallic hydrogen that produces different field geometry than the deep dynamo operating in the bulk of the metallic interior. Two dynamos, potentially operating at different depths, driven by different physical mechanisms, producing overlapping magnetic field contributions that sum into the complex asymmetric pattern Juno measured. Earth has a single core dynamo. Jupiter appears to have at least two interacting dynamo systems, and their behavior across geological timescales, whether Jupiter's magnetic field reverses polarity the way Earth's does, whether the great blue spot drifts or evolves, whether the shallow and deep dynamos can fall out of phase with each other, are questions that a single orbital mission cannot answer. Juno's extended mission will continue gathering magnetic field data, but fully resolving the structure of Jupiter's internal dynamo requires decades of continuous measurement that no currently approved mission is designed to provide. Below the metallic hydrogen layer, as depth increases and pressure climbs toward the center, the models diverge sharply. Some predict a gradual transition into a denser, hotter fluid of mixed hydrogen, helium, and heavier elements with no distinct boundary. Others predict the presence of a discrete dense core, a remnant of the original rock and ice protocore that seeded Jupiter's formation, now compressed to exotic states of matter under pressures of tens of millions of Earth atmospheres and temperatures of 30 to 40,000 Kelvin. The distinction matters enormously. A compact, well-preserved primordial core would be evidence that the core accretion model is correct, and that the rocky seed survived 4.5 billion years of overlying pressure. A diluted, dispersed core, or no core at all, would imply either that no rocky seed formed initially, supporting the competing disk instability model of Jupiter's formation, or that the core was somehow disrupted and mixed into the surrounding metallic hydrogen during Jupiter's early history. Juno's gravity measurements added data that forced the models in a direction almost no one had predicted. The answer was not a compact core. The answer was not no core. The answer was something that had no clean name in the existing literature, and it pointed toward an event in Jupiter's ancient past, violent enough to have permanently restructured the interior of the largest planet in the solar system. In the summer of 2011, NASA launched a spacecraft the size of a basketball court toward Jupiter. It carried no camera as its primary instrument. It carried a gravity science experiment, a magnetometer, a microwave radiometer capable of penetrating thousands of kilometers below Jupiter's cloud tops, and a suite of particle and plasma detectors. It was called Juno, and when it arrived at Jupiter on the 4th of July, 2016, inserting itself into a polar orbit that would carry it repeatedly over both of the planet's poles at altitudes as low as 4,200 kilometers above the cloud tops, closer than any spacecraft had ever flown to Jupiter. It began returning data that systematically dismantled the existing models of what Jupiter's interior looks like. The first major surprise came from the gravity measurements. Juno carries an extraordinarily precise radio science instrument that tracks minute variations in the spacecraft's velocity by measuring Doppler shifts in its radio signal transmitted back to Earth. As Juno passes over different regions of Jupiter's interior, the gravitational pull from mass concentrations below the cloud surface tugs on the spacecraft at slightly different rates. By analyzing these tiny accelerations and decelerations with precision down to fractions of a millimeter per second, scientists can construct a map of how mass is distributed inside Jupiter. The technical term is gravitational harmonics, the mathematical coefficients that describe the asymmetries in a planet's gravitational field, which in turn reflect the density structure of its interior layers. What Juno's gravity data revealed was that Jupiter's interior does not rotate as a single rigid body. On a rocky planet like Earth, the deep interior and the surface are mechanically coupled. They rotate together, barring the slow differential motion between the liquid outer core and the solid mantle. Jupiter's cloud bands were known to rotate at different speeds depending on latitude. The equatorial regions rotate slightly faster than the polar regions, and each jet stream band has its own rotation rate. The assumption had always been that this differential rotation was a shallow atmospheric phenomenon, confined to the outermost weather layer, and that below some depth, the planet rotated uniformly. Juno's gravity data showed that this assumption was incorrect. The differential rotation, the variation in rotation speed with latitude, extends to a depth of approximately 3,000 kilometers below the cloud tops. 3,000 kilometers of Jupiter's outer atmosphere rotates not as one body, but as a series of nested cylinders, each spinning at a slightly different rate, aligned with Jupiter's rotation axis in a pattern that fluid dynamics theorists call deep zonal flow. Below 3,000 kilometers, the differential rotation abruptly stops. The interior beneath that depth rotates essentially as a rigid body. The transition is sharp. The physical reason for that sharp transition at 3,000 kilometers is magnetic braking. Below that depth, the conductivity of the hydrogen, which is transitioning toward the metallic state, becomes high enough that the magnetic field threading through it resists differential rotation. Any layer trying to rotate faster or slower than its neighbors experiences a magnetic tension force that pulls it back toward uniform rotation. The magnetic field acts as a coupling mechanism, locking the deep interior into rigid body rotation, while the outer 3,000 kilometers of atmosphere remains free to develop differential flows driven by convection and Jupiter's internal heat. 3,000 kilometers sounds deep. By Earth standards, it is staggering. The radius of Earth itself is only 6,371 kilometers. But relative to Jupiter, whose radius is 71,492 kilometers, 3,000 kilometers is the outermost 4% of the planet. Everything in the weather layer humans have spent centuries observing through telescopes. Every jet stream, every storm, every cloud band, the great red spot itself, occupies the outermost 4% of Jupiter's radius. Below that thin shell, the planet is a different regime entirely. Then Juno's gravity data addressed the core question directly, and the result blindsided the planetary science community. Standard models of Jupiter's interior, built across decades of theoretical work refined through the Voyager and Galileo missions, predicted one of two possibilities. Either a compact, dense core of rock and ice surviving from Jupiter's formation, occupying roughly 5 to 10% of the planet's radius and containing somewhere between 0 and 10 Earth masses of material, or effectively no core at all. A scenario in which any primordial rocky seed had been dissolved into the surrounding metallic hydrogen over billions of years of high-pressure, high-temperature interaction. The gravity harmonics from Juno were inconsistent with both possibilities. The data required a core that is not compact and not absent. It is dilute, spread out. The heavy elements, rock, iron, water, silicates, that should theoretically form a concentrated central mass, are instead distributed across a region spanning approximately 30 to 50% of Jupiter's total radius. 30 to 50%. The core, if that word even applies to such a diffuse structure, could contain between 30 and 100 Earth masses of heavy elements, but they are mixed into the surrounding hydrogen and helium rather than concentrated into a distinct rocky sphere. The boundary between core and mantle, a boundary that is sharp and well-defined on every rocky planet and even on ice giants like Uranus and Neptune, does not appear to exist inside Jupiter in any clean sense. The scientific term for this structure is a dilute core, or sometimes a fuzzy core. Neither phrase adequately captures how strange this is. A planet 4.5 billion years old should, according to the dominant models of planetary evolution, have settled into a state of compositional stratification over geological time, heavy elements sinking toward the center under gravity, lighter elements rising, the whole interior sorted into distinct layers the way oil separates from water in a bottle. Jupiter's interior appears to be, at least partially, unmixed. The heavy elements in the core region are distributed through a volume thousands of kilometers across rather than segregated into a clean central mass. Something disrupted the settling process. Something either prevented stratification from completing or reversed it after it had already occurred. The leading explanation, developed and formalized in a study published in 2022 in the journal Nature by Shangfei Liu and colleagues at Sun Yat-sen University, proposes a planetary collision. Early in the solar system's history, within the first few million years of Jupiter's formation, when the solar system was still densely populated with large planetesimals and planetary embryos, a body comparable in mass to several Earth masses struck Jupiter at high velocity. The impactor, which researchers estimate had a mass somewhere between 10 and 50 Earth masses in the most probable collision scenarios, did not simply add its mass to Jupiter's exterior. It punched through the outer hydrogen envelope and penetrated to the core. The energy of the collision, which would have been measured in units comparable to the total solar luminosity sustained over millions of years, shattered and dispersed the compact primordial core. Heavy elements that had settled to the center over millions of years were ejected outward and mixed into the overlying metallic hydrogen, creating the diffuse, extended heavy element distribution that Juno's gravity measurements now detect. The collision also injected thermal energy into Jupiter's deep interior on a scale that would have significantly affected the planet's subsequent thermal evolution. How quickly it cooled, how its convective structure organized, possibly even how its magnetic dynamo developed over the following billions of years. Jupiter's current magnetic field asymmetry, its anomalous internal heat flux, and its dilute core may all be downstream consequences of a single violent event that occurred before Earth even existed as a rocky body. The implications extend beyond Jupiter itself. If giant planet formation routinely involves large impactors disrupting primordial cores, then the interiors of giant exoplanets detected around other stars, bodies whose internal structures astronomers attempt to infer from their mass-radius relationships and atmospheric compositions, may be far more complex and varied than any model assuming smooth, undisturbed layering can account for. The collision hypothesis does not make Jupiter anomalous. It suggests that the solar system's most dominant planet bears physical scars from its violent youth that are written into its gravitational field, readable only by a spacecraft precise enough and close enough to sense them. Juno was precisely that spacecraft. The data it returned has not closed the question of Jupiter's interior. It has replaced one set of uncertainties with a more detailed, more physically constrained, and in certain ways more deeply puzzling picture. The dilute core's exact extent, its precise composition, the degree to which convective mixing continues to stir it today, versus the degree to which it has stabilized into a settled configuration. These remain open. The collision model itself, while the leading hypothesis, has not been observationally confirmed in detail. Alternative explanations, including primordial disk instability formation scenarios that never produced a compact core in the first place, have not been entirely ruled out. But there is something else in Juno's dataset that the collision model does not fully address. Something in the upper atmosphere, in that outermost 4% of Jupiter's radius where all the visible dynamics occur, that the microwave radiometer detected in the equatorial region, hundreds of kilometers below the ammonia cloud tops, that does not fit the circulation patterns the models predict. An anomaly, a region of unexpectedly ammonia-rich air rising from depths far below any weather system, organized into a structure too regular and too deep to be explained by simple convection. Its origin is unclear. Its energy source is unclear. And its relationship to whatever happened to Jupiter's core 4.5 billion years ago, if any relationship exists at all, is one of the open questions now sitting at the center of active Jovian research. Jupiter's moons number at least 95 confirmed bodies as of the most recent catalog. 95 worlds orbiting a single planet, a figure that exceeds the number of planets orbiting the Sun by a factor of more than 11. The sheer census of the Jovian system is staggering, but the number alone understates the reality. These are not uniformly small, inert rocks. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo Galilei in January of 1610 and remain, 4 centuries later, among the most scientifically significant objects in the entire solar system. Galileo watched them move. Night after night, he tracked their positions and recognized that they were orbiting Jupiter, not Earth. In one observational sequence, he had produced the most powerful empirical argument yet assembled against the geocentric model of the cosmos. The moons of Jupiter, visible through a primitive refractor no more powerful than a modern child's toy telescope, had consequences for the entire intellectual architecture of Western civilization. Io is the most volcanically active body in the solar system, not the most volcanically active among the moons. Among all bodies, planets, moons, dwarf planets, everything. Its surface is covered by more than 400 active volcanic centers. Lava lakes of silicate magma, some hundreds of kilometers across, sit exposed on its surface at temperatures exceeding 1600 degrees Celsius, hotter than any lava produced by any volcano on Earth. Plumes of sulfur dioxide erupt hundreds of kilometers above the surface, arcing in graceful ballistic trajectories through Io's near-vacuum atmosphere before raining back down and coating the landscape in yellow, orange, and white sulfur compounds. The result is a surface that looks unlike anything else in the solar system. A world of violent, vivid color resurfaced so rapidly by volcanic activity that impact craters, which mark the surfaces of virtually every other solid body in the solar system, are essentially absent on Io. The surface is too young. The lava covers them faster than they can accumulate. The energy source for this volcanic inferno is not radioactive decay, as on Earth. It is tidal heating. Io sits deep inside Jupiter's gravitational field, orbiting at a distance of approximately 421,000 kilometers, closer to Jupiter than our moon is to Earth. As Io moves through its orbit, Jupiter's immense gravity flexes and deforms the moon's interior rhythmically, just as the moon's gravity raises tides in Earth's oceans. But Io is not alone in that orbit. Europa and Ganymede also exert gravitational tugs on Io, locking the three moons into a precise orbital resonance. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This resonance, called the Laplace resonance, prevents the orbits from circularizing. Io's orbit remains slightly elliptical, which means the magnitude of Jupiter's gravitational pull on it varies continuously as it moves closer and then farther from the planet. The differential tidal force stretches and squeezes Io's interior on every orbital cycle of approximately 42.5 hours. The friction generated by that repeated deformation produces heat, enormous amounts of heat. The total heat output of Io from tidal deformation is estimated at approximately 100 terawatts, roughly 6 times the total heat flow from Earth's entire interior. 100 terawatts, continuously. Produced not by nuclear reactions or residual primordial heat, but purely by the mechanical kneading of a moon inside a gravitational field. Europa, the next moon outward, receives a weaker version of the same tidal energy, and that weaker dose produces one of the most compelling scientific environments in the solar system. Europa is slightly smaller than Earth's moon, with a surface of water ice fractured into enormous plates, separated by dark reddish-brown ridges of material that is welled up from below. The surface temperature at Europa's equator reaches approximately negative 160 degrees Celsius. It is bitterly, lethally cold. But beneath that frozen shell, which is estimated to be between 15 and 25 kilometers thick depending on location, tidal heating maintains a global ocean of liquid water, an ocean in direct contact with a rocky seafloor. The volume of that ocean is estimated at roughly 3 times the total volume of all of Earth's oceans combined. 3 times. Contained beneath an ice shell on a moon smaller than our own, orbiting inside the radiation belts of a gas giant 628 million kilometers from the sun. Liquid water, a rocky seafloor, chemical energy from tidal heating. These are, on Earth, the conditions under which life originated near hydrothermal vents at the bottom of the ocean. The chemistry is not guaranteed. The biology is not assumed. But the physical and chemical prerequisites that produced life on Earth exist, in some form, in that subsurface ocean. The Hubble Space Telescope detected water vapor plumes erupting from Europa's southern hemisphere in observations published in 2012 and confirmed in subsequent observations. Material from the subsurface ocean potentially venting through fractures in the ice and ascending hundreds of kilometers above the surface. NASA's Europa Clipper spacecraft, launched in October 2024, is currently en route to the Jovian system and will arrive in 2030, where it will conduct at least 49 close flybys of Europa, probing the ice shell thickness, the ocean's salinity and chemistry, and the activity of any plume systems it can detect directly. If life exists in Europa's ocean, it has had no contact with sunlight since the ocean formed. It has existed in total darkness under kilometers of ice, sustained entirely by chemical gradients and tidal heat. The implications of that possibility, and it remains a possibility, not a confirmation, extend far beyond Jupiter. Ganymede, the third of the Galilean moons, is the largest moon in the solar system, larger than the planet Mercury. Its diameter of 5,268 kilometers exceeds Mercury's by approximately 8%, though its lower density gives it less mass. Ganymede is the only moon in the solar system known to generate its own magnetic field, a miniature magnetosphere nested inside Jupiter's enormous one, creating a complex region of interacting magnetic fields that produces its own auroral zones, visible in ultraviolet light, where charged particles cascade down Ganymede's field lines and excite atmospheric gases into luminescence. The Hubble Space Telescope detected these auroras in 2015, and their behavior, the way they rock back and forth in response to Jupiter's magnetic field, provided indirect but compelling evidence that Ganymede also harbors a subsurface saltwater ocean, which would conduct electricity and damp the expected oscillation of the auroral bands. The ESA spacecraft JUICE, Jupiter Icy Moons Explorer, launched in April 2023 and will enter orbit around Ganymede in 2034, becoming the first spacecraft to orbit a moon other than Earth's own. Callisto, the outermost Galilean moon, presents a surface that is the oldest and most heavily cratered terrain in the entire solar system. Every impact that struck Callisto over 4.5 billion years remains preserved there because Callisto has experienced virtually no geological resurfacing, no volcanism, no tectonic activity, no tidal heating strong enough to alter its landscape. Its surface is a direct record of the bombardment history of the early solar system, a frozen archive of violence written in craters stacked upon craters, some dating back to the period of late heavy bombardment that scarred every solid body in the solar system between 4 and 3.8 billion years ago. Where Io is reborn daily by volcanic fire, Callisto has been unchanged since before complex life existed on Earth. These 4 moons, one burning with tidal volcanoes, one hiding a global ocean beneath kilometers of ice, one generating its own magnetic field and concealing another ocean, one preserving 4.5 billion years of cosmic history in undisturbed craters, are not a representative sample of what moons are supposed to be. They are not geologically inert, cratered rocks. They are worlds with internal oceans, active geologies, and magnetic fields, all sustained by the gravitational energy of a planet so massive that its tidal forces replace the nuclear heat that powers geological activity on rocky planets. Jupiter does not merely occupy a position in the solar system, it is an energy source. It generates heat inside its own moons through gravitational mechanics alone, sustaining environments that, on at least 2 of those moons, may satisfy every known prerequisite for the existence of liquid water and chemical energy simultaneously. The Voyager 1 spacecraft, departing the Jovian system in March of 1979 after its closest approach, looked back at Jupiter from a distance of 1.5 million kilometers as it accelerated toward Saturn. The images it returned showed a planet of violent, organized beauty, banded, turbulent, enormous, glowing with internally generated warmth against the absolute cold of interplanetary space. Those images were the last any human instrument saw of the Jovian system until Galileo arrived 16 years later. In the years between, Jupiter simply continued, its winds grinding through their circuits, its great red spot rotating, its moons orbiting in their locked resonances, its metallic hydrogen ocean churning in the dark, its dilute core sitting at the center of it all, bearing the physical scar of a collision that predates every living thing that has ever existed on Earth. The solar system's largest planet, the solar system's most volcanically active body, the solar system's largest moon, the solar system's most likely candidate for extraterrestrial liquid water, the solar system's oldest preserved surface, all within a single gravitational system, all within the domain of one planet. And yet for all of that, for all the spacecraft, all the orbital mechanics, all the microwave radiometry and gravity science and magnetometer passes at 4,000 kilometers altitude. The most fundamental question about Jupiter's relationship to Earth remains unanswered with any certainty. Did Jupiter make complex life on this planet possible? Or has it spent 4.5 billion years as an indifferent gravitational engine, as likely to direct a civilization-ending impactor toward the inner solar system as to deflect one away from it? The data does not resolve the question cleanly. The models disagree. And the answer matters, not merely as an academic point of planetary science, but because every star in the galaxy likely has its own Jupiter-scale body at some orbital distance, And those bodies are shaping the habitability of every rocky world orbiting those stars in ways we are only beginning to understand how to measure. The Juno spacecraft completed its primary mission objectives years ago. It was never supposed to still be operating. Its original orbital insertion in 2016 was designed around a mission plan of 37 orbits, after which the spacecraft would be deliberately deorbited into Jupiter's atmosphere to prevent any possibility of contaminating the Jovian moons with terrestrial microorganisms. The mission has been extended repeatedly. As of early 2026, Juno has completed more than 60 close passes of Jupiter, collected data on the Galilean moons during targeted flybys, and returned more information about the interior structure, magnetic field, and atmospheric dynamics of Jupiter than all previous missions combined. It will eventually end. The spacecraft's components degrade under Jupiter's radiation. Its orbit evolves. At some point, the trajectory will carry it into the atmosphere, and the spacecraft will be gone, vaporized by the same pressure and heat gradients it spent years measuring from the outside. The data it has already returned will take decades to fully analyze. Some of the most significant papers produced from Juno's datasets have not yet been written. The scientists who will write them are, in some cases, still in graduate school. That is the actual pace of planetary science, not the pace of news cycles or academic grant cycles or the attention spans of any individual career. The pace of the science matches, in some strange proportional way, the pace of the phenomena being studied. Jupiter has been doing what it does for 4.5 billion years. Understanding it completely will take longer than any single human institution has yet existed. The question of Jupiter's role in the origin of life on Earth is not a poetic speculation. It is a live scientific problem with competing quantitative models that produce different answers depending on the assumed orbital architecture of the early solar system. The Grand Tack hypothesis, developed by Kevin Walsh and colleagues and published in Nature in 2011, proposes that Jupiter did not always occupy its current orbital position at 5.2 astronomical units from the Sun. In the early solar system, when the protoplanetary disk of gas still existed, Jupiter migrated inward under the gravitational torque of that disk, moving from its formation location to approximately 1.5 astronomical units, inside the current orbit of Mars. Then Saturn, forming behind it, caught up in an orbital resonance with Jupiter, and the two planets' coupled gravitational interaction reversed Jupiter's migration, driving both planets back outward to roughly their current positions. This inward and then outward migration, the Grand Tack, would have had consequences for the inner solar system that are still being assessed. As Jupiter moved inward, it would have truncated the outer edge of the rocky planetesimal disk that was building the terrestrial planets, potentially explaining why Mars is so much smaller than Earth and Venus. It formed from the depleted outer remnant of a disk that Jupiter had already swept through. As Jupiter moved back outward, it would have scattered outer solar system material, water-rich carbonaceous asteroids and comets from beyond the snow line, inward toward the young Earth, potentially delivering a significant fraction of the water now in Earth's oceans and the organic chemistry that preceded the origin of life. If the Grand Tack model is correct, the water you are made of may have been delivered to Earth by Jupiter's gravitational influence. The carbon in your cells, the nitrogen in your proteins, the complex organic chemistry of life's building blocks, all of it potentially scattered inward by the migration of a planet 3 times further from the Sun than Earth is now. The Grand Tack remains a hypothesis. It is well supported by dynamical simulations and is consistent with multiple constraints from the composition of meteorites and the size distribution of the terrestrial planets, but it is not confirmed observationally in a way that rules out competing models. Alternative orbital histories for Jupiter exist in the literature, and the degree to which Jupiter's migration actually contributed to Earth's water budget is a question that the planetary science community has not resolved. But the direction of the research, the questions being asked, the datasets being assembled, points consistently toward a single conclusion. Jupiter cannot be cleanly separated from the story of Earth. The two planets formed in the same disk, from the same raw material, under the influence of the same stellar radiation and gravitational dynamics. Jupiter finished forming first, and has been exerting gravitational influence on everything else in the solar system ever since. The rocky planets, including Earth, formed in the gravitational environment that Jupiter created. The water in Earth's oceans arrived via trajectories shaped by Jupiter's gravity. The chemical complexity that made life possible was assembled, at least in part, from material that Jupiter's gravity moved across the solar system. This is not a comfortable or simple relationship to describe. Jupiter has not been a guardian. It has not been a threat. It has been a gravitational engine operating without intent across timescales that dwarf the entire history of multicellular life on Earth, and the effects of its operation on this planet have been neither purely beneficial nor purely destructive, but deeply intertwined with the conditions that made this world what it is. Galileo Galilei, looking through a 20-power telescope from Padua in January of 1610, recorded 4 points of light near Jupiter that changed position from night to night. He recognized their significance within weeks. They were moons, bodies orbiting another planet, proof that the Earth was not the center of all celestial motion. He was placed under house arrest for the remainder of his life for defending that conclusion. The irony is not merely historical. The moons he discovered, the same 4 moons now being studied for subsurface oceans, active volcanism, and auroral magnetic fields, were the instrument of his intellectual downfall and the foundation of the observational astronomy that eventually produced everything that followed. Newton's laws of gravitation, the calculation of orbital mechanics, the development of spacecraft trajectories, the design of the Juno mission itself. Every piece of data Juno has returned traces a direct intellectual lineage back to 4 points of light Galileo tracked across a winter sky more than 400 years ago. The current Great Red Spot, which formed in 1831 according to the most rigorous current analysis, has been rotating continuously since before the first photograph was ever taken, since before the telegraph, since before the steam locomotive crossed a continent. It has completed approximately 1,200,000 full rotations since it formed. Each rotation takes between 4 and 6 Earth days. Each rotation carries winds faster than any hurricane in recorded human history, around a circle wider than the diameter of Earth itself, and it is smaller now than at any point in recorded observation. Whether it will survive another century, another decade, or whether it will dissolve into the jet stream that has sustained it for nearly 200 years, no current model can say with certainty. The storm does not know it is being observed. Jupiter does not know spacecraft are orbiting it. The physics operates identically whether anyone is watching or not. The metallic hydrogen churns, the magnetic field precesses, the tidal forces knead Io's mantle, the ice of Europa creaks above an ocean that has been liquid for billions of years in total darkness, 3 times further from the sun than the distance at which Earth orbits. There is a measurement problem at the heart of planetary science that Jupiter makes explicit. The object being studied is orders of magnitude larger than any instrument that can be built to study it. Juno, a spacecraft the size of a basketball court, orbits a planet 1,321 times the volume of Earth. The gravity harmonics that reveal the dilute core are extracted from Doppler shifts measured in fractions of a millimeter per second. The magnetic field asymmetry that hints at 2 interacting dynamos is detected by a sensor the size of a briefcase. The atmospheric anomaly in the equatorial region, that deep column of ammonia-rich gas rising from hundreds of kilometers below the cloud tops, was detected by microwave emissions too faint to observe from Earth. Every piece of knowledge about Jupiter's interior has been won against the resistance of scale, distance, and the sheer opacity of a world that has no surface to land on and no core to drill toward. What remains unknown about Jupiter is not a list of minor technical gaps. It is the central structure of the planet, the exact composition and spatial extent of the dilute core, the energy budget of the atmospheric anomaly detected in the equatorial zone, the long-term stability or evolution of the dual dynamo system generating the asymmetric magnetic field, the precise mechanism by which the Great Red Spot has maintained itself for nearly 2 centuries, and the conditions under which it will eventually cease, the degree to which the Grand Tack migration actually occurred, and what it contributed to Earth's chemical inventory. The question of whether Europa's ocean contains the chemistry, and whether that chemistry has produced the biology, that would mean life in this solar system did not begin and end on one small rocky planet orbiting at 1 astronomical unit. These are not small questions waiting for incremental data to fill small gaps. They are fundamental questions about the nature of the largest planet in the solar system, about the origin of life's building blocks on Earth, and about the conditions under which habitable worlds form and persist around stars. Jupiter has been in the solar system for 4.5 billion years. Humanity has been pointing instruments at it for 416. The first spacecraft reached its vicinity 47 years ago. The most capable spacecraft ever sent to study it is still transmitting. Europa Clipper is en route. JUICE is en route. The science is not closing in on a final answer. It is opening onto a larger set of questions than anyone working in planetary science 50 years ago had the instruments to even formulate. Every answered question about Jupiter reveals the outline of 10 more that could not previously be seen. That is not a failure of the science. It is what science looks like when the object of study is large enough, old enough, and complex enough to exceed the reach of any single generation of instruments or researchers. There is a point in Jupiter's orbit, the same point it occupies every 12 Earth years as it completes one full revolution around the Sun, when Jupiter is at opposition, directly opposite the Sun from Earth, and closer to us than at any other point in its orbit. At that point, Jupiter shines in the night sky at a magnitude of approximately -2.9, brighter than any star visible from Earth, bright enough to cast a faint shadow on a clear night. It has been doing this at 12-year intervals for as long as Earth has existed, for as long as the first photosynthetic organisms were altering Earth's atmosphere, for as long as animals have had eyes to detect light, long before any eye existed to see it. It will continue doing so long after the last instrument we have sent to study it has fallen silent.